In our third scenario, we are going to examine the effect of more sending and receiving pairs and more shared routers on the paths to the destination in the network. Assume 4 nodes with 4 unidirectional connections. We use the same notation of lambda n for original data sending rate, lambda prime n for original data plus retransmitted data, and lambda out for the rate at the receiver. Connections A to C and D to B share router 1. Connections A to C and B to D share router 4. C to A and B to D share router 3, and C to A and D to B share router 2. All links have capacity R, and all routers have finite buffer space. If a packet sent from A to C passes router 1, there is still a possibility it will encounter congestion. Note that the different paths will have different congestion patterns in each of their routers. For example, router 1 might not be congested in this example because connection D to B is idle and only connection A to C is using the link capacity at this router. But router 4 might be busy because B to D is sending at high capacity and exhausting router resources. So, if packet experiences congestion on router 4 and is dropped, the transmission capacity used at router 1 to send it to router 4 is a wasted capacity because the packet is eventually dropped and it needs retransmission, and that means router 1 will have to send it again. In multi-hop networks with multiple connections sharing links at different points, as we saw, with increase in the transmission rate due to increased competition for link capacity, the drops and further retransmissions that follow might cause drops in another point in the network. This is because of wasted capacity on previously traveled paths up to the point of previous congestion. This behavior will drag down the end-to-end throughput towards reaching 0 when sending rates at high end of shared capacity. This is a huge cost imposed by congestion conditions on a multi-hop network.